having discussed what are infinite series, sum to infinity, sum to n terms and so on, sequence of partial sums, convergence and divergence criterion, and we have discussed two tests for infinite series, namely the nth term test and the Cauchy criterion for series. Now, we can look forward to the other tests which are available for checking the convergence and divergence of a given series. So, welcome to this session. We can see two important series which are of a very relevance in our study. The first one is prove that the series summation 1 upon n square converges. So, we can see a proof of this. There is a rigorous proof available. We have to prove that summation 1 upon n square converges. This is the question. So, first let us look at this series as such. Summation 1 upon n square is nothing but 1 plus 1 by 2 square plus 1 upon 3 square plus 1 upon 4 square and so on. So, as we have discussed in the previous class, summation 1 upon n is a divergent series. Here also a similar type of manipulation is made in order to prove that this series is convergent. So, let us look at the terms of the series. The first one is 1 itself. The two terms 1 upon 2 square and 1 upon 3 square are replaced by the terms 1 upon 2 square and 1 upon 2 square itself. So, what happens to the LHS? The LHS is 1 upon 2 square plus 1 upon 3 square. 3 is greater than 2, and so 1 upon 3 square and 1 upon 2 square gives a less than or equal to symbol here, because this ratio is much smaller than this ratio, because 3 square is larger than 2 square. So, when you take the reciprocal, the inequality gets reversed. Similarly, if you take 1 upon 4 square plus 1 upon 5 square plus 1 upon 6 square plus 1 upon 7 square and replace every term, every higher term with the least term here, we will be getting 4 upon 4 square, and that is exactly equal to 1 by 4. And this is exactly equal to 1 by 2. So, rearranging or replacing the terms of the sequence using these, we get this series 1 plus 1 by 2 square plus 1 by 3 square plus etc. is less than 1 plus 1 upon 2 plus 1 upon 2 square plus etc. Now, look at the right side series. That is a very famous series, which is the geometric series we have already discussed in the previous class. Geometric series with common ratio r equal to 1 by 2, which is less than 1, and we have seen in the last class this series 1 plus 1 by 2 plus etc. converges to a finite value which is exactly equal to 1 by 1 minus 1 by 2, that is 2 you will get. So, we can see that this is a series which is bounded above by 2. So, we are getting the result 1 plus 1 by 2 square plus 1 by 3 square plus etc. is bounded above by 2. Or in other words, the sequence of partial sums which we had discussed is bounded above by the number 2. And just have a look at the sequence of partial sums. The first partial sum is S1, which is 1. S2 you will be having 1 plus 1 by 2 square. S3 you will be having 1 plus 2 square plus 1 by 3 square. So, look at the terms that is getting increased. So, we can see that each n minus 1 is added with a positive quantity to get the next Sn. So, Sn minus 1 plus 1 by n square gives you Sn, and so it is getting increased. So, sequence Sn, if you closely examine, is a monotonically increasing sequence bounded above by 2. Bounded above by the number 2. So, in the previous session we had discussed, when we discussed the sequences, we had discussed a theorem which is called the monotone convergence theorem, where we had said that a monotone increasing sequence converges if it is bounded above, and it converges to the supremum of that sequence. So, we can say that since sequence Sn is monotonic increasing and bounded above by 2, this sequence of partial sums converges to 2, and in other words this series also converges to 2. So, this series converges to 2, and 2 is the limit. So, that is how we prove this series summation 1 upon n square converges. A very similar proof can be applied to show that in general summation 1 upon n power p converges when p is greater than 1. Okay. So, that is the proof. I am not going to the proof of this part. A similar proof will give you this result. Now, we have the important test, which is called the direct comparison test. The direct comparison test says that if sequence xn and sequence yn are two sequences such that 0 is less than or equal to xn less than or equal to yn for n greater than or equal to k, it need not be true for every number k or for every n, it need not be true, but after some particular value it should hold, because at the end the two sequences should be comparable. That is the meaning of this. Then if the larger series, or if we add this term which is larger than xn, we are getting a larger series on this side and a smaller series on this side. So, if the larger series summation yn converges, then automatically the smaller series also converges. And if in the reverse order, if sigma xn diverges, then sigma yn diverges. So, this is the direct comparison test. So, if the larger series converges, the smaller series also converges. If the smaller series diverges, the larger one also diverges. So, I am leaving the proof as an exercise to you. You can look at the proof in the textbook. The next important comparison test that we have is limit comparison test, which says that again we are starting with two sequences xn and yn, be two positive sequences. So, remember that there should not be any negative term in the sequence. So, they should be positive sequences such that limit of the ratio xn by yn, the ratio of the nth terms of the sequences is equal to some number r, and that limit exists. Then, so limit of xn by yn indicates that limit n tends to infinity xn by yn is equal to r exists. Then, if r is a non-zero finite quantity, then summation xn and summation yn converges or diverges together. Converges if sigma xn converges if and only if summation yn converges, and vice versa. So, we can see that if this ratio is going to a finite quantity, then finite non-zero quantity, then the two series sigma xn and sigma yn both converge or both diverge. And if the ratio is going to 0 as n tends to infinity, then what happens? So, we are having the limit xn by yn as the ratio. So, if r happens to be equal to 0, then we are having xn by yn, the ratio is going to 0 as n tends to infinity, which means that the denominator is much heavier than the numerator. So, obviously summation yn is the larger sum compared to summation xn. So, it is something like the direct comparison test that we have here. So, if r is equal to 0 and if the larger series converges, then definitely the smaller series also converges. So, that is what is meant in the limit comparison test. So, again the proof is quite simple. I am leaving the proof for you. So, these two are very important tests that we have to keep in mind whenever we are using these two in solving problems in real world as well. So, whenever it comes to testing the convergence of an infinite series, these two results becomes very helpful in finding the solution. So, let us see the first example. Prove that the series summation 1 upon n square plus n converges. So, given such a question, what you have to keep in mind is, we are given problem number 1, summation 1 upon n square plus n. So, we are asked to find whether this converges or not. So, remember that the direct comparison test as well as the limit comparison tests only says that whether the given series converges or not. It will not give you the sum of the series. So, we have to apply some other techniques to get the sum, but we can very well say that whether it converges or diverges. So, we are asked to find whether this given series converges. So, you take the nth term as some un, which is equal to 1 upon n square plus n, and you try to find or you analyze this number given or analyze this term given, so that you can find out a higher term which you know, very well know, that it converges or diverges. So, here the denominator is given to be n square plus n, where n is a natural number. So, whenever this natural number is added to n square, this is definitely greater than n square, because you are adding some number which is greater than 1 to this. So, 1 upon n square plus n is obviously less than 1 upon n square, and therefore, you can take your Vn to be 1 upon n square, so that therefore, un is less than or equal to Vn. So, un is less than or equal to Vn you have obtained, so that you can apply the direct comparison test. And so, by direct comparison test, if the larger series sigma Vn converges, then the smaller series sigma un also converges. This is what direct comparison test says. And what about the convergence of sigma Vn? Sigma Vn is nothing but sigma 1 upon n square. So, in the beginning of this class itself, we had discussed the importance of this series. Summation 1 by n square converges, we had proved that. So, this converges, and hence the given series sigma 1 upon n square plus n also converges by direct comparison test, and that completes the proof of the first problem. So, this is how we solve this question. Now, we can do the second problem. Prove that the series summation 1 upon n square minus 2n plus 1 converges. So, let us see whether we can apply the same method as we have done in the previous problem. So, here the question is problem number 2, summation 1 upon n square minus 2n plus 1. So, as in the previous case, the previous problem was 1 upon n square plus n. So, we could very well write n square plus n is greater than n square, so that we could write 1 upon n square plus n is less than 1 upon n square, and we were able to apply the direct comparison test very quickly. But here the nth term un in this problem, the nth term un is nothing but 1 upon n square minus 2n plus 1, which we are not so sure whether it is less than 1 upon n square for every value of n, because the denominator contains a negative notation as well, n square minus 2n plus 1. So, we are not sure whether we can write like this or not. So, in this case direct comparison test is not that easily applied, and so we go for limit comparison test. So, by using limit comparison test, for limit comparison test what we require is limit n tends to infinity xn by yn or un by vn should be a finite non-zero value. So, this was our intention, or this is what we need to get, or we need to apply in limit comparison test. So, given your un equal to 1 upon n square minus 2n plus 1, when you apply limit n going to infinity, when n becomes larger and larger, there should be something in the numerator which cancels these n's off. Then only we will be getting this as a finite quantity. Otherwise, what happens if you directly put n tends to infinity, this will go to 0. So, we need some term here in order to get the ratio to be a finite non-zero value, we need to cancel these n's off. So, the technique that we use is take out the maximum powers of n both from the numerator as well as the denominator. So, taking the maximum powers of n both from numerator and denominator, there is nothing to be taken from the numerator, it is only 1 there. So, we take Vn to be 1 upon n square, because n square is the maximum power of n which can be taken out from the denominator. So, Vn we are taking as 1 upon n square. Then what happens if you take the ratio un by Vn, this will be nothing but 1 upon n square minus 2n plus 1 divided by 1 upon n square. So, that will give you into n square. So, that n square comes as the numerator. So, when you take out the n square outside from the denominator, we get 1 minus 2 upon n, because already there was an n here, we are taking n square outside. So, a denominator of n comes plus 1 upon n square. So, this n square and n square will get cancelled, you will be getting 1 upon 1 minus 2 upon n plus 1 upon n square. Now, as n tends to infinity, what happens? These two terms goes to 0. So, this and this goes to 0, which means you will get it as 1 as n tends to infinity, and 1 as we know is a non-zero finite quantity. So, summation Vn and summation un will converge or diverge together. Summation Vn is a summation 1 upon n square, which we know it is convergent, and hence the given series also converges by limit comparison test. So, that is how we prove the second problem. So, looking at the problem, you have to identify whether you have to apply direct comparison test or limit comparison test. That is very important. The third example is prove that the series 1 upon n factorial converges. So, again 1 upon n factorial means problem number 3, summation 1 upon n factorial. So, n factorial means the nth term is un equal to 1 upon n factorial. So, as we discussed in the case of limit comparison test, we have to pick out the terms containing n outside, maximum powers of n outside. So, is that possible in this case, because how many n's will be there? This is something like we are having 1 upon 1 into 2 into 3 into etc. up to n. So, just previous term to n will be n minus 1, the next previous term will be n minus 2 and so on. So, there are many terms containing n. So, we have to take out n from all the terms in order to take the maximum power of n outside. So, that is not so appealing or not so useful for our limit comparison test, and so what we use is we will go for direct comparison test. So, just look at the terms of the series. un we can write as 1 by n factorial, and we can say that this is less than 1 by n square for n greater than or equal to 4, because the first few terms are 1 upon 1 factorial, which is 1. The next term is 1 by 2 factorial, which is 1 by 2. The next is 1 by 3 factorial, which is 1 by 6. The next is 1 by 6 into 4, 24. So, writing the corresponding terms 1 upon n square, you can have 1, 1 by 4, 1 by 9, 1 by 16. So, you can see that 1 by 2 is greater than 1 by 4, 1 by 6 is greater than 1 by 9, but 1 by 24 is less than 1 by 16. So, this from this onwards, this happens to be less than or equal, less than. Okay. So, that is why we are writing something like this, an expression something like this. So, 1 upon n factorial is less than 1 by n square from n greater than or equal to 4. But as I told you in the beginning of infinite series, even if you add a few terms or even if you take a few terms from the infinite series, that is not going to affect the convergence or divergence of the infinite series, because we are adding infinite number of terms together. So, even if we are starting from n equal to 4 onwards, that does not make any problem. We need to concentrate more on the end part, tail part of the series. So, from n equal to 4 onwards, this is true, and that is enough for our direct comparison test. So, by taking Vn equal to 1 upon n square and using the direct comparison test, summation un converges if summation Vn converges, larger series converges, then the smaller series also converges, and here sigma Vn is equal to summation 1 upon n square converges, and hence the given series summation 1 upon n factorial also converges by direct comparison test. So, we can apply direct comparison test to show that summation 1 upon n factorial converges. So, that completes the proof of the third problem. Now, looking at the last example, example number 4, prove that the series summation 1 upon root n plus 1 diverges. So, what happens to this series is that, so far we were looking at only the convergent series. Now, we can see an example of a diverging series. Problem number 4, summation 1 upon square root of n plus 1. So, un is nothing but 1 upon root of n plus 1. Here also, because it is a root of n plus 1 in the denominator, we are not in a position to take a term which is converging or diverging on the other side. So, we can take Vn is equal to 1 by root n, but the problem is because root of n plus 1 is strictly greater than root n, and so we can apply 1 by root n is 1 by root of n plus 1 is less than 1 by root n. But the problem is we have learnt that summation 1 upon n raised to p converges if and only if p is greater than 1. So, here the value of p is 1 by 2. So, if the value of p is 1 by 2, it is less than 1, and so the series will not converge. So, it diverges. And direct comparison test does not tell us something which is convincing for us or something about the series. If the upper series or if the larger series diverges, what happens to the smaller series? That is not obtained directly from direct comparison test. So, we cannot go for direct comparison test in this case, and hence we go for limit comparison test. So, un by Vn gives you 1 upon root of n plus 1 into root n, which is equal to root n divided by root n into 1 plus 1 by root n, or square root of 1 plus 1 by n. So, this root n and root n will get cancelled when you take the ratio, and as n goes to infinity, we can see limit n tends to infinity, un by Vn is nothing but 1, which is a non-zero finite quantity. And what does limit comparison test say? If summation, if the ratio limit un by Vn or xn by yn, whatever it be, goes to a finite non-zero quantity, both the series converges or diverges together. So, if we have summation Vn is equal to summation 1 upon root n, which can be written in the form summation 1 upon n power 1 by 2, diverges, and hence by limit comparison test, summation un also diverges. So, that is how we can prove that the given series diverges. So, in this class we have learned two important tests for convergence, which are called the direct comparison test as well as the limit comparison test, and we have seen a few problems where we can apply both these tests. And also remember that there are many more tests available which we will be discussing in the coming classes, and these two tests are for positive term series, or if the terms of the series are non-negative, then we can apply these two tests. Limit comparison test strictly says in the statement itself that the two sequences should be of positive terms. So, that we have to always keep in mind when we apply the direct comparison test and limit comparison test. Thank you.